Okay, let's go. We said waves. Now, what is a wave? A wave is a disturbance. A wave can be defined as a disturbance. Disturbance on the board. Disturbance. You said A, you still look at it too. And you're saying A. You say, is it ordinary disturbance I cannot, I cannot spell. A wave is a disturbance that is produced at a point and transfers energy to another point without the permanent displacement of the molecules of the medium. Now, how do we do this? Types of wave. No, next is classifications of wave. So I'm going to give you a broad classification. Let's make it into a chart. So we have waves. Now waves are divided into two. Now we're going to follow this classification. Waves are divided into stationary waves, and what? Stationary and progressive waves. Stationary and what? So all of our transverse waves that we'll be doing, they are progressive. Okay. So those progressive waves are now split into two. We now have the transverse waves. No. It is first mechanical and electromagnetic. So under electromagnetic we have, no, it's like this. Transverse and longitudinal, right? Longitudinal. It's not longitudinal, longitudinal. And before you say, once I did not pronounce it, longitude, unless it's longevity. What's this? It's not longevity or longevity. So our transverse waves are divided into mechanical. So some mechanical waves are transverse, okay. Mechanical waves and what? EM waves. What are EM waves? We know the light. What's the formula of me? Electromagnetic waves. Our longitudinal waves are divided into only mechanical. So a longitudinal wave can only be longitudinal, never. A longitudinal wave can only be mechanical, never electromagnetic. Is that okay? So let's describe each type. Stationary waves. This is a wave that is produced when two waveforms traveling in different directions but on the same plane interact. Number two, progressive waves. This is a wave. We've not even drawn it. Some people are complaining of writing. Some, they've not even drawn. Okay, so we said, now let's take the stationary waves. This is a wave that is produced when two waves moving in different directions. This is a wave that is produced when two waves moving in different directions. No, you can't. Oh, so look at finished before we even said when two waves traveling in different directions are superimposed as shown below. She won. Yeah, when I was even talking to her, that she has won. Oh, this one now came from somewhere. Me too. All right, let's go, please. Okay, so now let's create a plane here using dashes. So two waves, they're traveling on this plane. This is called a waveform. This is called a what? So this one is traveling like this, and this other one is always traveling like this. Now notice two things. Now the way I should draw it is such that the, no, I didn't draw it well. The way I'm supposed to draw it is such that something like this. Do you know why? So that when they meet, one will just be forming the, I will define all those things. So the crest, the other will be forming the trough. Is that okay? So let's go again. When two waves, we'll still take stationary waves on its own, or is that okay? Because that's what leads us to sound waves. All right, but this one, we just want to understand what stationary wave is. So when two waves, so let's say waveform A, and waveform B. So when waveform A and waveform B interact, they're going to form something that looks like this. These are our plane. They should cross on this plane. Is that okay when you're drawing those? All right. So put that down. Yes, this is what they form when they interact. It's called a stationary wave. Okay, I know what came to your mind. Interference? Okay, we'll talk about interference. Interference does not mean they come from different directions, really. They can, in fact, for interference to occur, they must be produced from the same source. We did coherent sources when we started. Coherent sources. Coherent sources means both of them appear from the same beginning. Now, there's something I must show you here. Okay, so let's write that. Let's define this stationary wave. We said what? That is produced. And draw this thing now. You must draw it. Yeah, you really have to draw it. See, draw it anyhow. There are some people here that are drawing skeleton. So, no, Tolu usually gets it. Is that boy that's drawing now? Tolu even got it more than me. Tolu even got it more than me. Ah, okay. Yours is better than Tolu's. This is rubbish here. See your this thing. They are. It's not. I should look at you. Yeah, I don't want to cry too. All right, let's go. Are we done? When these two waves meet, I won't wait for you. Have I started playing? So all those. When two waves meet, when the two waves meet, the trough of one of waveform A, yeah, the trough. This is how to spell trough. I'm going to define what those terms mean later. Is that okay? The trough of one coincides. Is it coincides with or coincides the? Coincides the crest of another, of the other, of waveform B. The trough of one of waveform A coincides the trough of anyone you use, though, whether the crest coincides the trough or trough coincides the crest. This is what I'm bringing up. See, this one, when you say wave like this, that's the crest. When you see this part like this, it's called the trough or depth. That's okay, we call it trough or depth. I mean deep, high. Do you understand? You can hear people say the wave high. So this is the wave's high, this is the wave's depth. Do you understand? Above a fixed point. Do you understand? This is the point of minimum deviation. Do you get it? So this is the wave's high, the wave's depth. We are going to talk about Doppler. Okay, okay. Now listen, just listen first. This wave I, so the wave I, the maximum point is called the trough. Is that okay? And here, the lowest depth is called the crest. Do you understand? So they will coincide to form a stationary wave. For them to form a stationary wave, they must what? Coincide. So when they coincide, this is what they form momentarily. Do you get it? So they form this, and the point where they interact, there's intersection of those waves is the point of no displacement. The point of what? And it's called the what? I promise you. Maybe the mu. No, it's not true. But this is how you remember. No displacement. Do you understand? Are you liking me now? Okay, you don't like me. Okay, while the midpoint between those two nodes, we call it antinode. You must understand this thing when we get to sound wave. You must understand it. So that's why we're building on it now. So antinode node. So here we have what? Antinode. Here we have what? Node. Here we have what? 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 Yeah, no. Busy high. You people, I like my students. Okay. So wave can actually bend round obstacles. Do you understand? So and that is called diffraction. So waves, as I'm predicting. Okay, can you hear me now? How did it happen? The wave is progressive from my mouth, is longitudinal from my mouth, but actually it's bending around me, the obstacle. I'm not an obstacle. But it's bending around me. That's why someone from that class will see here because it can bend around this thing. And we're going to show how it happens actually. All right, let's go. Number 2, progressive wave. A progressive wave is one that has a point source and is continuous. And is what? Continuous. That's the meaning of wave. A progressive wave. I mean, I needed not to put that point source above, just so you know that it has a source. All right, so it is continuous. Now let's talk about the types. So progressive wave is divided into transverse and longitudinal. No, you don't have to write it again. You've written this thing. So just go A. So this is 1, 2. 2A transverse wave. A transverse wave is 1. Okay, let's give an example of those stationary waves. Stationary waves are waves in tube, right? Waves on string. Waves in tube, that's wind instrument. Wave on string. That's also a wind instrument, I hope you know. So, but wave on a string. For example, the guitar strings. If you pluck it, does the wave pass more than that string? No, right? So it's a stationary wave. Do you understand? It has 2 points where it is fixed, 2 fixed points. You know what I'm saying? So it's called a stationary wave. Then progressive wave. Our sound wave, as I'm making now, which other wave again? Electromagnetic wave. You understand? They are all what? Progressive. Now let's go. Transverse wave. These are waves, or this is a wave which travels in a direction. This is a wave which travels in a direction that is perpendicular. This is a wave which travels in a direction that is perpendicular. Don't say pepe, okay. Perpendicular to the point of propagation or to its source of propagation. This is a wave which travels in a direction that is perpendicular to its source of propagation or point of propagation. Is that okay? All right. So what does that mean? It means that if the source of propagation is like this, let's say this is the source of propagation. So the source of propagation is going like this, your own wave will be going like this. Your own wave will be going where? Here. If the source of propagation is going like this. Does that make sense? Perpendicular means 90 degrees. Is that okay? So let's give an example. An example is the ripple tank, right? Ripple tank. How do you spell ripple? Double P Ripple tank. Tank. You know what a ripple tank is? Now see, as I want you to look at this. And are you getting it? All right. When you get home, take take a bucket or a large bowl. I would prefer you use a large bowl so that you can see this thing very well, very clearly. Now inside it, pour water. Make sure the water is still. What does still mean? Not moving, calm. God bless you. So now take another droplet from what from somewhere. Do you understand? Droplets. Yes, I was saying something about droplets yesterday. No, no. Yeah, God bless you. Make you surface tension. That's the reason why substances form droplets. Is that okay? Because of what? Surface tension. Right. Okay, but I now said that's liquid. That's what I did. So put your hand, plunge your hand inside water and release a drop into that water that is still. What will you see? You see wave that is spread, right? You see something spread, right? That's what we call water wave. Do you get it? But how did if you don't use water, you can use stone, or if you don't want to, I just want it to be water to water so that you know. You can use stone or an object, any small object. Throw it into that water. If that thing doesn't sink, let's assume that thing doesn't sink. As that thing drops in the water, say throw a light paper. I didn't say it. I said, for example, Jesus Christ. Who brought this boy? All right, let's go. So you throw, are we here? So you throw something inside that can float. Let's assume something. Yes, give me an ice, an ice cube. You throw it inside that water, eh? What would be the displacement, the direction of displacement of the distance? So this is your hand dropping it. Eh? Is that okay? Your hand drops it. Now once it enters the water, where will it go? How will it go? It will go up and down because it will not sink, right? Ice will not sink as it flows, right? So it will go up and down, or down. Thank you. Down and okay, it will not go up. That's true. So it will go down and up before it now, rests. Is that okay? So what happened? The direction of movement in that water is what? Up and down, right? But the wave that it is spreading is going sideways. And in fact, that up and down is to show you that to and fro movement, when we get to simple harmonic motion, if I was supposed to start it with simple harmonic motion, up and down movement is a wave movement. Is that okay? For example, if I'm going up and down like this, all I need to do is displace either the frame or the person. If I displace the frame, you see that it will create a wave. If I displace the person, all I'm doing is move my hand up and down. But what did I create? A waveform. Is that clear? It's becoming clear, right? All right. That's just how waves are formed. We're talking about how waves are formed. All right. So, but what kind of wave is this? A transverse wave, because the motion that creates it is in the direction of motion that creates it is perpendicular to the direction of the wave. So the motion that creates it is up and down, up and down. But the wave itself is going side to side. For example, in our ripple tank system, it's going to form a concentric waveform, right? All right. So that you see ripples like this, right? Spread abroad. Is it becoming clear? Good. So what kind of wave is that? Transverse wave. So we know transverse wave now. A wave that will travel in direction that is perpendicular to the direction that the motion that creates it. Is that okay? All right, e.g., you've written water wave as in ripple tank. All right, give me longitudinal wave. Okay, another example of transverse wave is electromagnetic wave. Is that okay? Then your sound wave. For some people, there was one time I taught some set of students, they told me that sound wave was a transverse wave. All right, so I'm here to tell them. All right, sound wave is a longitudinal wave. Sound wave is what? On that day, one of them was not sure. As everybody was, some of them were right, is a transverse wave. Let's pause. So now, a longitudinal wave is a wave that travels in a direction parallel. In a direction that is what? Parallel to its source of propagation. The waves are traveling in a direction that is parallel to its source of propagation. Don't worry, we'll soon stop the class. But I want I want us to get to terms used in waves so that we'll call it a day there. Is that okay? Terms used in waves so that you understand very well. Because it's not okay that we just treat this kind of waves and you don't understand those things that you've seen. How did they get to be? Okay, I've explained how one became, right? From some continuous periodic motion. Is that okay? You just be going like this. And once you are going like this, you are in a wave system or a circular motion. Do you know we did the relationship? You know it's a circular motion, right? Let me show you something. Let's say I'm going like this. What am I drawing? A circle, right? So this is my circle now, right? Facing you. Now let me bend my circle. My circle is now like this. Now if you were on a 1D system, what motion will you be seeing of my hand? My hand is just going like this to you. Translation. But we don't call it translation, it's a to and fro movement, but it's a special form of translation because of course we're still moving. Okay? Is he on? Okay, so now let's go. Longitudinal. Okay, yeah, I'm just trying to relate all those things that have to do with waves for you. So that when we be going back to how it is, because we mentioned things like cycle, so you'll be confused as how is this thing a cycle? That is how it's a circle. It's basically a circle. Do you understand what I'm saying? It's basically a circle. Like I'm going. There's a way. Yes. God bless you. Now if I type, give me please pause it. The motion of this ID is what? Circular. But, so you see it now. It's going to be circular as I'm moving. Circular. This is a circle. It's forming a circle, right? It's forming a circle. Now, by the time I turn it to the frame of reference changes. If you couldn't see, the reason why it's not very apparent is because you can see in 3D. If you couldn't see in 3D, if you were seeing in 1D, one dimension, all that you'll be seeing is, you will not be seeing it when it goes to the back because this part will be obstructing it. So all that you'll be seeing is this guy going from here to here. Do you understand now? So any periodic motion like this is also a circular motion. It's also circular. Or it can be related to a circular motion. Do you understand now? And that's the way wave 2 is. Because I said we are going like that or like that, and you displace only one of the medium. What will you see? A wave form. Do you understand? All right. Let's go. Longitudinal wave. Okay, we've defined it. So example of a longitudinal wave is a sound wave. Because the direction in which it travels is always parallel to the direction of the of propagation. So let's draw a person's mouth. Whose mouth could this be? Let's draw a person's mouth. Let's use an actual mouth, What is that? DMB, what's wrong? How do you draw it? Okay, this is success, for example. Are you here? So now, it makes noise. Yeah! Head boy! And then, are we here? You now see, wave will be propagated from here. Now, the waveform that goes out of here, want to pick only one line of wave. Is that okay? So, want to pick one line of wave. What you will see is this. The way you are able to hear, the reason why you are able to hear is because this wave is traveling in a straight direction, number one. And you're able to hear him because the wave he made is basically, he pressurized the air molecules that are close to his mouth. Is that okay? By pressurizing them, the air molecules that were dispersed before, that were just spread abroad, normally in equilibrium, they became stressed and tightened together. You know, stress is also pressure. Compressive stress, force over area, pressure. All right. So he pressurizes it. At that time, when he pressurized it, there was This place was diffused. Pressurized, diffused. So after a while, as immediately it creates the sound, the next layer receives that pressure. At that time, this one will be diffused. This one will be what? Pressurized. Those parts, okay. At that time, when this one was pressurized, this one was what? Diffused. After a while, this pressure will move here and become what? Pressurized. And like that, we have diffuse pressure zones. We call them high pressure zone. We call them what? High pressure zone. It's not pressure, so high pressure zone. All right. All right. So these portions of high pressure, or we call them, or these ones that we call high pressure zone, we call them compressions. Somebody say compressions. Compressions. And then this portion where there are no this we call them rarefactions. Or a refraction, anyhow you call it. Rarefactions. Eh? Rarefactions, please. Do you get it? The point of low pressure is what? Low pressure zone. High pressure zone. This corresponds to the wave that we make on a string, for example. If I held a string at one point and you held it at another point, and I just oscillate it about a fixed point, what do you see? Yes? Oh, zero. Where were we, please? So this is this thing that we held here, and then I pluck it like this. No, this is not plucking. This whatever. I just so are you with me? No, I remember the right term. I remember it. Okay, so what you form is this. Let's bring it up. We're done with all of this, right? Okay, we are still on it. Oh God. Okay, so this is what you see when you disturb that rope. Is that okay? This is what you're going to see. So these portions here that are high here, they are portions of high pressure, right? These highs are, I call these wave highs. So these wave highs are the what? Are the high pressure zones. And these wave lows are the what? Low pressure zones. They correspond. No. Do you understand now? They correspond to the low pressure zone, the rarefactions. Do we understand now? All right. On this, so we're going to be considering this wave form. So this portion here is called the trough. It's called what? And this one is called the crest. All right. We'll soon get there. Just draw it and label that. Let's quickly define the rest. So now we have gotten to mechanical and electromagnetic. Yes, you can demand. I don't know. It's not even fine. All right, let's go. I didn't ask for time. All right, let's go. Mechanical wave. This is a wave that requires what? Mechanical medium. This is a wave that requires material medium for propagation. Somebody would. Common definition. This is a wave that requires what? For propagation. Example, sound wave. So sound wave is a what? A mechanical wave, yet a longitudinal wave. So it requires material medium. But another transverse wave that can be mechanical is water wave. Water wave does not form except there is a substance that creates it. So it requires, water wave is also a mechanical wave. Water wave is also a mechanical wave. Now, the next wave, electromagnetic wave. EM waves are waves that do not require material medium. EM waves are waves that do not require material medium for propagation. EM waves do not require what? No material medium. But this one requires material. Example of EM wave: X-ray, gamma ray, your Revox G rather. Revox G. Your infrared. All these your Revox G. You know what Revox G stands for? If you don't know what Revox G stands for, raise your hand. So I'll quickly go over it. radio wave, infrared wave, visible light, visible light, ultraviolet, X-ray, gamma ray. Then the visible light spectrum is the one we see, right? The portion of light that I will link a video in the description to show you where I've talked about visible light. Is that okay? But also know that visible light is the portion that we can see. The reason why we can see now, we can see each other putting on different shades of colors of clothes is because of visible light. Is that okay? So the visible light spectrum is between 400 nanometers and 700 nanometers. Is that okay? It also has its own spectrum. So from that 400, we have Roig Beef spectrum. Those are the 7 colors of the rainbow. R for O for Y for G for B for I for V for. No, it's easy. It's just easy. Listen. There was one thing I taught you the other day. Okay. See, you see, we call this radio wave and infrared. Look at something. Please, I want you to listen. I want you to understand it. There's no need to cram anything. See, infra. What does infra mean? Below. Do you get it now? So if I say infrared ray, it means it is below red. So the first wave under the visible light spectrum. Maybe it's not clear enough. Let me show you. It's a Revox G, right? So, and under the Revox is another band that we have that is called the Roig Beef. So this one is called the red, right? Red, that you call red color. And this one is called the what? Violet. I hope you know that their colors are not exactly colors. They are just waves of light. Do you understand now? Yeah. For those of you that don't know. The reason why that shirt is appearing red is because red is the only wavelength of that light, of the white light is what's causing that thing to be red. Is that okay? So when the white light incidents on it, that white light consists of ROYGBIV. Is that okay? So that cloth has properties that can absorb OYGBIV, but not red. So it will now reflect the red. Is it clear? The reason why things appear blue will be that what? It absorbs ROYGIV, but reflects, cannot absorb that blue, so it reflects it. Do you understand? And that's how we see. So I wanted to mention something now, red and violet. The wavelength, the portion of the wave spectrum that is lower than red is called the infrared. Is that okay? So this is called the infrared because the first one here you see is the red. Then the one that is higher than the last one here is what? Violet. So ultra means what? Higher or above. Is that okay? So ultraviolet ray. Does that make sense to you? That's how it is named. Is it clear? When you hear UV ray, that is ultraviolet. That's above violet. Violet is a color, you know, right? So above that color range or wavelength is, or frequency rather, or frequency is the ultraviolet. All right, let's go. Like I said, we are ending it, right? Okay, should we quickly define terms? Just small. All right. See you in the next video. God bless you.